I had never been introduced to the concept of entropy production until I came back to teach thermodynamics in 2020 after I retired in 2019. Now, I had been exposed to concepts of entropy and was able to analyze proposed processes and cycles based on some fundamentals that I was taught. But I found that this concept of entropy production that's provided by your author in your textbook is superbly elegant and easier to understand than some of the concepts of entropy that I was introduced. And but I found it very tough to learn, and so I'm going to try to go through some steps to help you try to understand and learn some of the fundamentals about entropy production, and then ultimately how to compute and determine a value for entropy production so that you can evaluate whether a proposed process or cycle is possible or impossible or possible and reversible. So let's go ahead and get started. I have found that the concept of entropy production is complex enough so that I have busted entropy production into 3 videos. This one is going to have to do with entropy production for closed systems undergoing a process. The next one is going to be entropy production rate for open systems. And then finally, I'm going to talk about entropy production for cycles, either a system that's undergoing one single cycle, or more realistically, a system that is performing a cycle over and over and over again at a steady rate. So let's look at entropy production for closed systems. But before we do that, let's take a little crash course and remind ourselves of things that we should already know or hopefully are learning and cementing in our minds before we move into entropy production. So here's my little crash course on what we covered in chapter 5 and the early parts of chapter 6. So, of course, remind you, this is a copy and paste slide, isn't it? Entropy is a property. And you'll remember that I tried to as smoothly and gently as possible introduce the idea of entropy by saying there's properties you already are familiar with and you know, and you have visualizations of those properties: pressure, volume, temperature. And entropy, I tried to say, let's visualize entropy, it's a property, as a measure of disorder, so that a low value for entropy S would correspond to something that's highly ordered. A small value of S would mean a highly ordered system, but a higher value of S would mean more disordered, less order, more disordered. And that would be a higher number, a high value of entropy. And so I hope you have a sort of a physical feel for that. And you also got familiar with dealing with capital S, the extensive property entropy, and little s, the intensive property for entropy. Let's see, little s had units: kilojoules per kilogram degree K, or BTUs per pound mass degree R. Then we defined how do you define entropy change? And so we started with entropy change, S2 minus S1, some process 1 to 2. We defined it in terms of an integral across an internally reversible path. And then we sort of moved back and said, okay, now we can define incremental change in entropy. ds is del Q over T, an incremental piece of heat transfer going across an internally reversible incremental path. Okay. And then remember, we took a little next steps. We multiplied both sides by T and integrated to say, okay, gosh, I think I see now that for a reversible process, I can visualize heat transfer on a TS diagram by the area under the curve. All right, so we're kind of getting comfortable with those ideas. Now we're going to introduce a new variable called entropy production, and I've written it down. This is Greek letter sigma. This is not the number 6. It's Greek letter sigma. please refer to it as sigma, entropy production. Now, here is where I'm going to say I started getting a little confused. I had to work very hard because I had to teach this material, right? And so you really have to learn it when you're teaching it and trying to explain to others. And I'll have to admit, the first time around, I didn't do a very good job, but I got better and better at it. So let's look at equation 5.2, and I'm going to try to tell you why I had a hard time grasping this thing. First was the word count of equation 5.2. It kind of blew my mind. So that was hard enough as it was reading these words. What the heck does all these words mean? So then I did discover in the textbook a little screenshot here of seeing that first bracket term is called the entropy change term, equals. The next term is called an entropy transfer term. More on that in a minute. All right. And then this last term in brackets, that's the entropy production term. And then I hooked, oh, that's sigma. That's what we're talking about, sigma, over in chapter 6. I think I'm starting to get it now. Okay. That helped, but it didn't get me to the promised land. And so now I'm going to tell you, I'm going to kind of relate the little story of how I improved my understanding of sigma. So I got this thing that this third term is called sigma. So here's, next I'll try to reduce the word count. Okay. This big bracket thing, I tried to reduce the word count saying, well, that's the entropy change term of the open or closed system. The entropy change of the open or closed system. Okay, that's going to be kind of like capital S2 minus capital S1. That's kind of like that. Equals entropy transfer across the system boundary. And it says across the system boundary. That's got to have something to do with heat transfer. Okay. Because remember, there's two types of energy that go across the system boundary, right? Heat and work. Know that heat transfer is related to entropy very, very intimately. And then the last term, well, that's the entropy production term, sigma, and it's the result. Sigma is going to be some number that resulted from a proposed process or an observed process. One or the other of those, a proposed or an observed process. That's the entropy production term, sigma. Okay, I feel a little better. But I still wasn't super comfortable, but it finally dawned on me that I started realizing as an engineer, I'm trying to drive towards calculating sigma, the entropy production. And I thought, well, in my experience, if I can get what I'm looking for on the left-hand side of the equal sign, I can start dissecting what's on the right side and I can get to the left-hand side. That helped me. And so I rearranged equation 5.2, both in my mind and on paper. I said the entropy production equals two terms. So this is what I'm trying to find. Sigma equals two terms. The entropy change amount minus, so you see here, I moved this term over to the left. You see that? So entropy change minus this entropy transfer term that I didn't fully understand yet. All right. But anyway, I started feeling better about this. And then I realized the third statement of the second law is sigma is greater than or equal to 0. Simple as that. So sigma has got to be a number that's greater than or equal to 0. It can't be less than 0. So that's the statement of the second law. I was feeling a little better that I think I might be able to teach this thing now. So let me move my picture down here because this is going to end up being a busy slide. I've tried to distill this statement of the second law, sigma greater than or equal to 0, into 4 sentences. And so here's the first sentence I came up with. It says the entropy produced as a result of any possible process must be greater than or equal to 0. So that's sort of a word statement, an English word statement of this equation here. Next sentence. If the entropy produced as a result of any process is greater than 0, then the process is possible, but it's irreversible. Okay, that makes sense. So if sigma is greater than 0, the process is possible, but the process has got something going on that's irreversible. Still possible. If the entropy produced as a result of any process equals zero, if it exactly equals zero, then the process is possible and it's reversible. So reversible and possible. Okay, I'm getting somewhere. And then finally, if the entropy produced as a result of any proposed process, I added a word, proposed process, not process. If the entropy produced as a result of any proposed process is less than zero, then the proposed process is impossible. That's very important. And that's the way, so the importance of being able to determine what is the value for sigma, that can help you address. So if a salesman says, I have a proposed process that I'd like to sell you. I'm not going to show it to you, but I'm going to want you to buy it and then I'll show it to you. But you got to come up with the money first. And here's what I propose. Here's the process that I propose. So if you're able to get that salesman's specifics of the process, and you can determine sigma, if you find out that it's a negative number, if it's less than zero, you go back to the salesman and say, you're not going to get any of my money because, and you can explain respectfully that what you're proposing to sell is flat impossible. And so you can respectfully address salespeople who will try to sell you impossible things, as well as meaningful people, well-meaning people who are trying to propose things with good meaning, but what they're proposing is just flat impossible. That's the power of being a good mechanical engineer. Okay, I hope that helps in getting a little more comfortable. You're getting more comfortable. What's sigma all about? I went back and dusted off a slide, and I said, I think this might help. So, is it possible, or let's categorize the question. Here's the question. Is a proposed closed system process possible or impossible? So that's a common way to pose a question. So here's a proposal. It's a closed system. It's going to undergo a proposed process. Tell me if it's going to be possible or impossible by evaluating sigma. All right. So let's say, okay, good. I've got information. I'm going to come up with sigma. There's two possibilities if the process is possible. If sigma exactly equals zero, the proposal is possible and reversible. You come up with sigma. If it's a number that's greater than zero, the proposed process is possible and it's irreversible. Now, the good part, if you come up with a sigma value for this proposed process and it turns out to be a negative number, you can respectfully explain that that proposal is impossible. And I can explain to you why. It violates the second law of thermodynamics. Okay, so I hope that this lower word count slide helps you see that this is the key to learning how to quantify if a proposed process is possible or impossible. This is going to be a very predictable quiz or test question, no doubt about it. Okay, so now what I want to do is rewrite equation 624 to illustrate something that's a pesky minus sign. So now we're jumping ahead to equation 624. And so I've taken a screenshot out of the book. Equations, now we're into chapter 6, equation 624, entropy production for a closed system. And here it is. So the entropy change term is capital S2 minus capital S1. Extensive property equals the integral from 1 to 2 of the heat transfer over Q over T across the system boundary. That's the entropy transfer term. I'm going to show you how to evaluate that in a minute, okay? Plus the entropy production term. And so, again, I had this tough time wrapping my head around equation 624, so I rearranged it. I rewrote it here on my own paper. So I solved for sigma. Sigma equals, well, let's move this to the left-hand side. So that's how I get this pesky minus sign, okay? And so the pesky minus sign is the integral across the system boundary. That's my little circle there, is looking at all places on the system boundary where I've got heat transfer of del Q over T. So the integral of the heat transfer terms divided by the temperature at which heat is being transferred okay, plus S2 minus S1. This is the entropy change term. So there you go. I felt so much more comfortable with this. The entropy production, what I'm looking for, equals minus the entropy transfer term plus the entropy change term. This just really helped me understand where I was going in evaluating entropy production. So I got it. This slide, I hope, helps you as well. So sigma equals minus the entropy transfer term plus the entropy change term. That minus sign is going to turn out to be pesky, and I'm going to try to show you how to get over your fear of that minus sign in front of that term. Okay, so the entropy change. So let's step through. I'm having to move my Zoom menu here so I can see my screen. Okay. Let's work through understanding the equation 624 terms. The entropy change term, capital S2 minus capital S1. Okay. So do you see that depending for any process, so capital S2 minus capital S1, extensive property, it can be a positive number, it can be a negative number, or it can be zero. It can be anything. Okay. So what you're doing is, you're using sigma to check to see if the proposed process is possible or impossible. At this point, you don't care if S2 minus S1, if S2 is bigger than S1, if S2 equals S1, or if it's less than S1. You just don't care, okay? It's an entropy change term of the closed system. And so here, notice my reminder. Capital S2 minus capital S1 for a closed system is M, the mass of the closed system, times little s2 minus little s1. I hope you got this. So we're just dissecting this one term, entropy change, S2 minus S1. It can be positive, negative, or zero, because what you're doing is you're checking sigma to evaluate the process, not just delta S. Sigma is different than S. Next term, the entropy transfer term. Okay. I'm going to give you some example problems that will clarify this. B means you've got to study as an engineer the system boundary. Where is heat coming in? Is heat leaving? And you got to account for all of those across the system boundary. And so remember in this equation 624, del Q over T, remember the textbook doesn't put in. And so you must remember that in the textbook, Q simply means Q in. And this is why it's paying off for me that I always write Q in. This is paying off for me. I hope it pays off for you. The term T, this term T usually applies to the surroundings temperature, whether you're adding heat to the system, the closed system, from the surroundings, or if you're rejecting heat from the system boundary into the surroundings, or a combination of both. Okay, so this T term, this temperature, is absolute temperature, and it applies to the surroundings temperature, not the system temperature. Okay, so very important. Although the word count is high here, I'm going to wiggle my cursor here. If the heat is flowing into the closed system, the entropy transfer term will be a positive number. So this integral, if the heat is flowing in, this resulting value is going to be a positive number. Okay. If heat is flowing out of the system, if Qn is less than zero, flowing out of the system, heat rejected, then this entropy transfer term will be a negative value. That's important. Okay, this is the entropy transfer term. You're going to get some number for this term. And it's going to have units kilojoules. It's going to have units of kilojoules per degree K. Simple example of calculating the entropy transfer term. So this is so important to understand. I'm not even going to do an example problem. I'm just going to calculate the entropy transfer term in an example. It says 60 kilojoules of heat Qn, 60 kilojoules of heat is transferred into the gas contained in a piston and cylinder from a heat source held at 300 degrees K. So I'm starting with a sketch. Determine the entropy transfer term for this process. So just entropy transfer, okay? We've got a closed system. Heat is going into the closed system. It just says it in the words. Here's my sketch. Qn 300K in the amount of plus 60 kilojoules. Okay, so this entropy transfer term is plus Qn divided by T, 60 kilojoules divided by 300K. So it's going to be plus 0.2 units, kilojoules per degree K. This is the entropy transfer term for this example. This can have some value. So a screenshot of this or absorbing this can help you. This is only the entropy transfer term. Okay, now let's do a full-fledged example problem. It says a gas with a mass of 2 kilograms is contained in a piston and cylinder. Heat in the amount of 80 kilojoules is added from a heat source held at 400 K. That's pretty hot, okay? During the process, the specific entropy, little s, of the gas increases, little s2 minus little s1. So during the process, the specific entropy of the gas increases by 0.25 kilojoules per kilogram degree K. And the question is, determine the entropy production, sigma, for this process. Let's go through numerically and do this problem. I've repeated the problem statement. I've started with a sketch. I'm showing heat flowing in from a temperature reservoir at 400 degrees K. I didn't write down what Q is numerically, but I see that it is 80 kilojoules into added from a heat source, okay, into the closed system. Closed system, mass is 2 kilograms. Little s2 minus little s1 is plus 0.25 kilojoules per kilogram degree K. Okay, got it. So let's go through all the numbers. I'm looking for sigma, left-hand side of the equation. That's what I'm looking for. I wrote down this, basically the screenshot of my governing equation. I didn't remember this equation. I had to go to my textbook and write it down. Okay, so we've got entropy production equals minus, here's my pesky minus sign, minus the entropy transfer term plus the entropy change term. All right, so let's go through the numbers. I've got minus. I put a bracket, right? So my bracket is Qn divided by T, both given in the problem statement, plus M times little s2 minus little s1. So you see the relationship here. Got it? Okay. Don't forget the pesky minus sign. So equals pesky, the minus sign in the brackets, plus 80 kilojoules divided by temperature 400 K. Okay. M, 2 kilograms, delta little s2 minus little s1 given. Okay. Turn the crank. Okay. So if I turn the crank on my calculator, I go through all the numbers and I get sigma equals plus 0.3 kilojoules per degree K. And I give myself a big check because I get a positive number. Okay, so that's good. And so what's the conclusion? So is there anything irreversible about this process? Yes. Sigma is a bigger number than 0. So this was not overall. So what we're doing is studying the overall process. Okay. So with the overall process, sigma is plus 0.3 kilojoules per degree K. And so our conclusion is the process is irreversible. So yes, it's possible. Let's do another one. A gas with a mat. So I've got a pesky toolbar that's open and I can't figure out how to get that off. All right, I've got it. Okay, I think I'm good. Excuse me. So example problem 2. A gas with a mass of 0.5 kilograms is contained in a piston cylinder. Heat in the amount of 40 kilojoules is rejected from the gas to the surroundings at 290 degrees K. Okay, that's a difference, isn't it? During the process, the specific entropy of the gas decreases by 0.2 kilojoules per kilogram. Wow, so little s2 minus little s1 is a negative number. Huh. Determine the entropy production sigma for this process. Wow, entropy is decreasing within the system. Huh. Let's study sigma and see if this process that's described in the problem, is it really possible? Is it possible at all? Because look, the entropy of the system is decreasing. All right, let's blunder ahead and see what we get. All right, so I've repeated the problem statement. I have drawn my sketch, and notice here I've shown 290. I am showing an arrow going in, okay, even though with our eyes we see that heat is rejected, but to make up for that, I'm showing that Qn is less than 0. That's critical on my sketch. Qn is less than 0. Our job is to determine the entropy production sigma. Sigma equals what? Well, minus the entropy transfer term plus S2 minus S1 of the system, entropy change. All right, let's knock off this term first. Do you see that capital S2 minus capital S1 is going to be M times S2 minus S1? And in fact, it's going to be a negative number here, isn't it? I'm looking ahead. It says the entropy of the gas decreases by 0.2. So look here in my numerics, I've put in a minus 0.2 over here for M times little s2 minus little s1. Now let's work on this entropy transfer term. Here is my minus sign. Here's my bracket. Okay, so now I've got Qn. I've got to be very careful. Qn is negative 40 divided by T, the temperature at which the heat is transferred, 290. So I can put 290 down there. All right, so now notice what I've got on my calculator work. I've got minus a minus. That's a plus. 40 over 290 in the plus direction, plus some terms. That looks like it's going to be half. It looks like it's going to be minus 0.1. So that's a half. So it's going to be negative 0.1 kilojoules per degree K. The kilograms and kilograms cancel out. So I do the math. I turn the crank on my calculator. Sigma is plus 0.0379 kilojoules per degree K. Well, that's bigger than 0. It's a number bigger than 0. So this process also is possible, and it's irreversible because sigma is greater than 0. You see how we did there? So we looked at 2 examples, one where heat was added, one where heat was rejected, and we both verified that both processes are not only possible as described, they're both irreversible. So that covers it. That covers what I needed to cover. I hope that my going on and on about the difficulty that even I had with understanding entropy production, and I tried to show you some of the tricks so I was able to get over the hump in understanding entropy production. I do find in my interactions with students that understanding entropy production is an extraordinarily difficult concept to grasp and then to execute. And so I do hope that this sort of lengthy explanation helps you get moving, because a lot of students at this point think that S2 minus S1, that the entropy change of the system, that the entropy can never decrease. That's not true. So the entropy of a system can decrease. The property S can decrease for a system in a possible process. The trick is that it's all about the heat transfer has to be rejected as well. So you can go through the numbers and see, yes, the entropy S2 minus S1 can be a negative number, but you've got to balance that with heat transfer out of the closed system. Okay, so hope that didn't blow your mind. So what's our recap? Entropy is a property. S is a property. Entropy production refers to a process, full process, where heat is being transferred from one location to another location at different temperatures. So understand the difference between entropy change, that's S2 minus S1, or little s2 minus little s1. Entropy transfer, that has to do with the heat transfer and temperature term. What's crossing the system boundary in terms of heat? And entropy production sigma. Entropy production sigma is the combination of entropy change and entropy transfer. And do remember that pesky minus sign. And so anyway, I tried to go through a couple examples, so hope you have a better understanding of how to determine sigma for a closed system undergoing some process 1 to 2. Again, these videos are starting to get a little more complex, aren't they? A lot more complex than Chapter 1 videos and Chapter 2 videos. However, once you get through Chapter 6, it's all about applications after that. So that's the good news. Coming up, entropy production I found to be so complex that I'm going to take you through another video where we look only at open systems undergoing steady state, steady flow processes. And so I'll do that to try to help and review how to make those computations as well.